Hello, this is Rick from MathX, and today we'll be going over the number 15 from the 2010 AIME II. Now, this problem was requested by a viewer, the same viewer who requested the AIME 15 from the 2019 test. If you could recall, in that video we discussed a complex topic, homotheties. But to solve this one, we just need to be creative when applying simple concepts and theorems. Nothing too complex. But we have to be able to apply these theorems in a way to solve a complex problem. Anyways, without further ado, let's just jump right into the problem. In a triangle ABC, AC equals 13, BC equals 14, and AB equals 15. Points M and D lie on AC with AM equal MC and angle ABD equals angle DBC. Points N and E lie on AB with AN equals NB and angle ACE equals angle ECB. Let P be a point other than A of the intersection of the circumcircles of triangle AMN and triangle ADE. Ray AP meets BC at Q. The ratio of BQ over CQ can be written in the form of M over N, where M and N are relatively prime positive integers. Find M minus N. So to solve this problem, the first thing we have to do is pretty much the same thing we did in the other problem. We have to draw the diagram. So the first step is to do the first directions. Draw a triangle and label its coordinates such that AC equals 13, BC equals 14, and AB equals 15. So just draw a classic 13, 14, 15 triangle with A, B, and C at their respective vertices. The next thing we have to do is the second phrase of the problem. Make sure we draw points M and D on line AC such that AM equals MC and angle ABD equals angle DBC. Well, first, since AM equals MC, we can see that M is quite clearly the midpoint. So we just need to identify a midpoint and draw it in and label it as M. So let's do that. Now that we clearly identified the midpoint of AC and labeled as M as the direction described, we have to find point D such that angle ABD is equal to angle DBC. That means that point D is probably the line where the angle bisector of the opposite angle B will hit the side AC. So we can put that in. Now, the question might be, where would this point D go? Would it go above M or below M? To figure out whether point D would go above M or below M, we just have to use some simple angle bisector theorem. Remember, AB is equal to 15 and BC is equal to 14. So the angle bisector would divide line segment AC in such a way such that the part below angle AB divided by the part below side BC would give us the same ratio of AB over BC. So since AB is 15 and BC is 14, the part below AB will give us 15x and the part below BC will give us 14x. So clearly it'll be further down than up. So it'll be below the midpoint of M. So we can label a point slightly below the midpoint of M as point D. Next, we got to do the next line in the instructions. Identify a point N such that AN is equal to NB, so the midpoint of side AB, and identify a point E such that angle ACE is equal to angle ECB. So basically the intersection of the angle bisector from C to side AB. First, we can identify point N quite simply just by trying to find the midpoint of the segment. So let's just do that first. Next, since it said that angle ACE is equal to ECB, we can once again use the angle bisector theorem to determine whether point E would be above or below point N. Well, we know that AC is equal to 13 and BC is equal to 14. So if we use angle bisector theorem, the two parts that the angle bisector from C would divide into are two line segments in the same ratio of 13 to 14, where the bottom part will be 14 and the upper part will be 13. So clearly it's going to go farther up than down, so it'll be above the midpoint, meaning that point E will probably lie somewhere across here. So we can draw this in as point E. Our next step, once we have all the points on the triangle laid out, we have to do what the problem tells us to do next. Find the intersections between the circumcircles of AMN and ADE. Remember, the circumcircles are just the circles in which the specific triangles are inscribed in. So we just need to be able to draw circles through these select points, AMN and ADE. And then once we draw circles through them, we can find out and label the point where they intersect as, besides A, as P. So let's just create some circles and see where they intersect at, besides A. So here we've drawn the circles of triangle AMN and ADE. So we see that they both intersect at this point over here. So we can just label this point as P. And now that that's done, we can perform a final step of the problem. Create a ray AP that meets BC at point Q. So just draw a line from A through this point P so that it'll intersect line BC at a point, and we'll label this point as Q. And just like that, we have our diagram done. Now we just need to find out what BQ divided by CQ is, and this is where the problem really begins. So to solve this problem, the first thing we need to acknowledge is that trying to find that BQ over CQ when all our information is really centered around here is going to be kind of hard. So similar triangles will really help us out in solving this problem. We can generate one similar triangle by drawing a line between M and N. As M and N are both the midpoints of AC and BC respectively, their sides are in proportion with the larger sides. Along with that, they share a common angle. So triangle AMN is similar to triangle ACB. Now, we see that line AP, which intersects BC into line segments that we need to find ratios of, also intersects line segment MN that we just drew in. So let's label this intersection with another letter. How about U? Well, we see that triangles AMN and triangles ACB are centered at the same vertex. And they're basically the same triangle, except one of them is just an enlargement of the previous smaller triangle. And we see that in order to get from AU to AQ, we just enlarge the triangle AMN to scale ACB and enlarge line segment AU to AQ. So that means that each of these parts, UN and UM, are also enlarged to BQ and CQ. And a similar idea to homotheties. So since we see that UN and UM are enlarged to form line segments BQ and CQ, the ratio of UN over UM is equal to the ratio of BQ over CQ. So in this problem, if we solve for what UN divided by UM is, we solve for what BQ divided by CQ is. So now we just need to think about the entire problems into trying to solve for UN and UN. And that makes it much easier since most of our information is centered around this point U instead of this point Q. So instead of focusing our efforts on parts of the triangle that we don't really have information on, by focusing our efforts on the parts that we do have information on, we'll be able to solve this problem much easier. So now on to solving for what UN over UM is equal to. Well, the first thing we can see is that in this triangle there are a lot of lines. But it almost seems as if AMPN could form some sort of quadrilateral. And so we see that is the case because points AMPN all fall in the same circle. So we can form a cyclic quadrilateral AMPN. So here we have cyclic quadrilateral AMPN. Now, you're probably thinking, what's so important about that? Well, cyclic quadrilaterals have unique properties. One of them being a lot of similar triangles inside of them. For instance, in this case, we can see that triangle AMU is similar to triangle NUP. This is because they have equal measures in one angle, angle AMU and angle NUP through vertical angles. And we also see that angles MAP and angles MNP are also the same because they both intercept the same arc. So if this angle and this angle are congruent to this angle and this angle, through AA similarity, we see that triangle MAU is similar to triangle NUP. We can also see that triangles MUP is also similar to triangle AUN because, once again, they share a vertical angle, meaning that these angle measures are the same, and angles PMN and angles PAN both intercept the same arc, meaning that angles PAN and PMN are also the same. So, since they share angles PMN and angles PAN, these two angles are congruent, and there's one vertical angle making another pair of congruent angles. Through AA similarity, triangles PMU and triangle NAU are both similar as well. Now, the good thing about similar triangles is with similar triangles, we can often find sides in proportion with one another. So, keeping this in mind, we can try to find out sides in proportion with our target sides, UN and UM. So, let's do that. So, if we exploit the second similarity, triangle PMU being similar to triangle NAU, create one of the relationships that we can write involving one of our desired sides, UM, is that UM divided by UA is equal to MP over AN because both pairs are corresponding sides of similar triangles. So UM over UA is equal to MP over AN. Using another similarity relationship between triangles MAU and triangles PNU, we can exploit AU again to solve for UM over UN by finding that AU divided by UN is equal to AM over NP. So we can write that as UA divided by UN is equal to MA over NP. And we can see that this works because, once again, these are just two pairs of corresponding sides on similar triangles. The good thing about these two relationships is that they both contain UA. So if we multiply both of these equations together, UM divided by UA equals MP over AN, and UA divided by UN equals MA over NP, well, multiplying the left-hand sides together would give us UM over UN, because the UA would cancel out, but nothing on the right-hand side would cancel out. So we get that UM over UN is equal to MP over AN times MA over NP. Well, the thing is, we already know a couple of these sides, MA and AN, because we remember M and N are the midpoints of their sides respectively. So MA would be half of the side AC, and AN would be half of the side AB. So we would get that UM divided by UN would give us MP divided by AN, which we deduce to be half of AB, and since we know that AB is 15, half of that would give us 7.5, so AN is 7.5, and times MA over NP. Well, we know that MA is once again the midpoint of side length AC, and since AC has a length of 13, MA will have half that side length, so half of 13 is 6.5. So, writing it clearly in one statement, for UN over UM, we can write UN over UM is equal to the reciprocal of 6.5 over 7.5, which is 7.5 over 6.5, which can be simplified down to 15 over 13, times the reciprocal of MP over NP, which is simply just NP over MP. So now all that's left to do is compute what NP over MP is, plug into the equation, and then we get what UN over UM is. And since we know that UN over UM is equal to BQ over CQ, solving for UN over UM will give us the answer. So let's try to solve for NP over MP to solve this problem. But first, I'm going to clear off some space to the right here because it's getting kind of cluttered up. So let's quickly do that. So now for NP over MP. Well, we can't really do anything about NP over MP as it is right now, but if we look at points E and D, we see that we can form some triangles. We can form MDP and PEN. And those triangles kind of look alike. So if we can prove that these are similar, we can probably exploit some similarity to compute the ratio between NP and MP. So let's just draw in some line segments to attempt to find out if triangles PEN and triangles PMD are similar. So to do that, we just have to connect the lines between D and P and E. So let's quickly do that. So now we have triangles PEN and triangles PMD. So let's see. If these two triangles are similar, they're either sides that are in similar ratios, or they share two angles with equal angle measures. Since our goal is to try to find the ratio between the side lengths, we can't really look at the ratios between the side lengths because we have to find that out ourselves. So let's look at the angles and to see if these two triangles share at least two angles with equal measures with each other. So let's think. Well, if angle PMD was x, that would mean that angle PMA would be equal to 180 minus x. Because, remember, it's a straight line, and the sum of angles on a straight line always add up to 180. So, PMDX, PMA, 180 minus x. Because we see that angles PMA and angles ANP are on the same circle. In fact, these angles are opposite vertices of a quadrilateral inscribed in a larger circle. Angles PMA and angles ANP are opposite angles in a cyclic quadrilateral. Now the deal with cyclic quadrilaterals is that opposite angles have to add up to 180. So that means that angles PMA and angles ANP have to equal to 180. Well, we know that angles PMA is equal to 180 minus x. So that means that in order for angle ANP to add with angles PMA to equal to 180, angles ANP is equal to x. So we can write that the measure of angle ANP is equal to x. So basically what we just did here is we found that the measures of angles ANP and the measures of angles PMD are the same. This angle is equal to this angle. And we proved it by exploiting a property with angles on a line and then using another property of cyclic quadrilaterals. So that's one angle that we found in common between these two triangles. We still need to find one more in order to prove that triangles PMD and triangles PEN are similar. So let's take a look at the next angle, angle ADP. Let's say that angle ADP is y. We can kind of go reverse of what we did with angle AMP, and instead of going to this angle next to it, we go to the opposite vertex of the cyclic quadrilateral. ADP is on another circle, along with point E. In fact, the whole quadrilateral ADPE lies on one circle. So since D and E are opposite vertices of this cyclic quadrilateral, the sum of their angles add up to 180. So since we denoted ADP as y, we must denote angle AEP as 180 minus y. And then, since AEP and PED lie on the same line, they also have to add up to 180. So if angles AEP is equal to 180 minus y, in order for the whole line to have an angle measure of 180, we see that angle PEB has to have an angle measure of y. So essentially, we've just reversed the steps we used with angles PMD and ANP. We first exploited the property of a cyclic quadrilateral and then exploited straight line to find out that angles ADP and angles PEB are the same. So we got another pair of equal angles. So since we got two pairs of equal angles through AA similarity, we can say that triangle PMD is similar to triangle PNE. Now, how are we going to use this to compute for NP over MP? Well, since NP and MP are corresponding sides of their respective triangle, the ratio between NP and MP is going to be the same as the ratio between any corresponding sides on these two triangles. So we can write MP over MP is equal to EP over DP, which is further equal to En over Md. Now, we're trying to solve for what NP over MP is, and we don't have any information about what EP over DP is. So EP over DP is kind of useless. But we can find out what En over MD is, because we know the relationship between D and E and M and N. D and E are the angle bisectors, and M and N are the midpoints. And by angle bisector theorem, it's pretty easy to compute the lengths of the parts of the angle bisectors. So we use the second relationship. NP equals En over MD. NP over MP is equal to En over MD. So now all that's left is to compute for En over MD. And this can be solved using some simple angle bisector theorem. En is just EB minus NB. Now, NB is the midpoint of side AB, so NB has half the length of side AB. So since AB is 15, NB, as we previously established, is 15 over 2. But to find out what EB is, we have to use angle bisector theorem, which basically states that this part divided by this part is equal to BC divided by AC. So essentially, EB is going to be BC over BC plus AC times AB. And since we know that BC is equal to 14, we can write this computation as BC 14 over BC plus AC, which is 14 plus 13 or 27, times AB. And AB is 15. So the computation becomes En is equal to 14 over 27 times 15 minus 15 over 2. Now, I'll let you do the computation on your own. And just multiplying and subtracting fractions, we get that En is equal to 5 over 18. So now, to do the same thing, but for MD, well, we use the same kind of idea. MD is equal to MC minus DC. And since we know that M is the midpoint of side AC, MC is just half the length of AC. So AC is 13, so MC is 13 over 2. Now, DC is slightly more difficult to find, because to use it, we have to do the same thing we did in finding En. We have to use angle bisector theorem. Angle bisector theorem, as I said before, states that DC is equal to BC over BC plus AB times AC. So if we plug in the numbers for all that, we get the computation BC, which is equal to 14, over BC plus 18, 14 plus 15, which is just 29, times AC, which is 13. And if we compute for that, just doing all the calculations out on your own, we get that MD is 13 over 58. So remember, En over MD was also the ratio between NP over MP. So this 145 over 117 is also equal to NP over MP. So we can substitute this value into this equation to find out what un over um is and solve the whole problem. So if we substitute into this equation, we get 15 over 13 times 145 over 117 is equal to un over um. So if you just be smart about your computations and calculate for the product of these two fractions, you'll eventually get 725 over 507 as your final result, your final answer for un over um. And as I've repeated many times before, un over um is just merely bq over cq. So 725 over 507 is equal to bq over cq. So since in the problem it wants us to find m minus n, we just do 725 minus 507, which will give us an end answer of 218. So thus, that's our answer to this problem. M minus n is 218. And just like that, we solved the number 15 from the 2010 AIME II.